Welcome, everyone. Thank you so much for joining us for OA Week 2023. My name is Sarah Flickinger, and I'm an Associate Research Scientist at the OAICC, and I'm also a member of the GOA-ON Secretariat. Before we get started, I just want to make sure everybody is aware that this session is being recorded and will be posted later on YouTube. OA Week is sponsored by 4 organizations. First, GOA-ON, the Global Ocean Acidification Observing Network. Second, NOAA, the United States National Oceanic and Atmospheric Administration. Third, the IAEA OAICC, the International Atomic Energy Agency Ocean Acidification International Coordination Center. And lastly, the IOC UNESCO, the Intergovernmental Oceanographic Commission of the United Nations Educational, Scientific, and Cultural Organization. So for a quick introduction to GOA-ON and OA Week before we turn this session over to our wonderful speakers. GOA-ON was established in 2012 and has grown immensely since then. So now in 2023, we have over 1,000 members from 114 countries. We have 9 regional hubs, which span continents and oceanographic regions, as you can see in this map here. And we'll be hearing from most of these hubs during OA Week. If you're not yet a member of GOA-ON, we welcome you to join by visiting www.goaon.org. So OA Week debuted in 2020 and returned in 2021 when events and conferences were postponed due to COVID-19. Following the in-person symposium on the ocean in a high CO2 world in 2022, GOA-ON is bringing back OA Week 2023 to maintain momentum around OA research and provide a virtual platform for the ocean acidification community to exchange our latest findings. We are thrilled to present a wide range of ocean acidification topics and speakers from around the world. So a few logistics before we get started. During the presentation, all participants will be in listen-only mode. We welcome you to type any of your questions for the speakers in the Q&A box, which is found at the bottom of the control panel on the right-hand side of your screen. We'll be monitoring these incoming questions and we'll pose them to the speakers during the question and answer section. For the discussion, you can also use the raise hand function, which you can find in the toolbox at the bottom of your screen, and we will call on you to ask your question directly, at which point you can unmute and speak directly with our speakers. So at this point, I am very pleased to introduce to you the moderator for this session, Masahiko Fujii, who is from the Atmosphere and Ocean Research Institute at the University of Tokyo. He is a professor at the International Coastal Research Center of the Atmosphere and Ocean Research Institute. He and his group are conducting research to understand the current status and future projection of the impacts of excessive anthropogenic CO2 emissions on coastal ecosystems worldwide and to develop countermeasures, both mitigation and adaptation. They are also conducting research to elucidate the local impacts on coastal ecosystems of extreme events such as storms and marine heat waves, which are expected to increase in frequency and intensity with the progression of climate change. Masahiko, the floor is now yours.
Yeah, thank you, Sarah, for the introduction. Hello, everyone. I'm Masahiko Fujii from the University of Tokyo, and I'm the moderator and also the first speaker. So let me share my slide. Do you see the slide?
Yes, we see your slides.
So this is a session about the ocean acidification in seas around Japan. We have the 4 speakers, including myself. And the aim of this session is to kindly ask you to know about the recent studies focusing on seas around Japan in terms of the ocean acidification. Yeah, so far, no serious impacts of the ocean acidification on marine organisms have been reported in the seas around Japan. But Obviously, the ocean acidification is progressing at a rate faster than the global average nearby Japan. So we do the monitoring and modeling. Monitoring to know the current situation of ocean acidification and the future projection to predict the future. Based on numerical modeling. So today, out of four presentations, three are focusing on monitoring, and one is mainly focusing on modeling, but one is a mixture of the kind of the monitoring and modeling. So there I'll show the current situation of the social acceptance, social impacts of the ocean acidification to the society. So the compared to the global warming, ocean acidification is less known by the society, but recently they come to know more. For example, there are many of my colleagues, including myself, showed up on the TV program and also the newspaper. And recently, this is the content last week. Finally, some private junior high school show the entrance examination. They treat ocean acidification. So the ocean acidification is getting to more popular, but still we don't know very much about them. Mainly because we don't have any direct impacts of the ocean acidification on coastal or the marine ecosystem directly. So, but in the future, no one knows. So we need to know about that. So today, there are many previous studies do the monitoring and numerical modeling. Those are examples of the studies focusing on the open ocean. The figure left is this is will be introduced by Hisashi Ono, fourth speaker, more in detail. But he and his group have been monitoring for long term, so more than 25 years along the 137 east and 165 east. This is Japan, so they're closer to Japan, but mostly in the open ocean. This is another example. So there, jump state. So this is Dr. Wakita's group. So they have been monitoring for last 25 years at two stations, Station North and K2. So this is another example of the open ocean monitoring in terms of ocean acidification. For the coastal regions, as long as I recognize, there are 33 monitoring sites along the coast of Japan. But actually, out of the 33, 23 stations have been deployed after 2019. So there are only 4-year monitoring history. So to know the long-term trend of ocean acidification, we need to keep the monitoring for next decades. So we are doing that, and some not enough, still not enough, but some monitoring data have been already provided to GOA-ON. Yeah, those are stations of which data have been available via GOA-ON. So there, this is kind of the background of our current studies. So today we will give the 4 presentations as shown here. So the first they're given by myself, and so the yeah, after the 4 presentations, we'll invite a discussion. Yeah, so the first I'll start my talk. So this is a this is a the talk there entitled "Observed and Projected Impacts of Coastal Warming and Acidification on Pacific Oyster Farming." Case studies in Hinase area, Okayama Prefecture, and Shizugawa Bay, Miyagi Prefecture in Japan. So they're done by myself and also the many colleagues. And I'd like to thank the several fundings, especially the Nippon Foundation Ocean Acidification Adaptation Project, which support many of our coastal monitoring. So there, first, why oysters? Yeah, not only we really like the oysters, but there obviously the oysters are second most important shellfish and aquaculture species in Japan, following the scallops. And oyster farming largely supports local fisheries industries in some prefectures, especially in Seto Inland Sea. This is located in the western part of Japan. In some prefectures facing on Seto Inland Sea, around 70 to the 80% of the total fisheries income by the oyster farming. So you can easily understand how important oyster farming is for them, the local people. But as oysters are calcifying species, so there can be the fear by the ocean acidification as well as ocean warming. So we really worry about the impacts of the oceans, combined impacts of ocean warming and acidification. Yeah, recently the ocean global warming is not only considered to be the long-term trend, but they enhance the short-term extreme events like marine heat waves, typhoons, floods, and so on. So such the phenomena can interact each other and then lead to the compound effects on oysters in the future. So in this study, we focusing on 2 sites. One in Hinase in Okayama Prefecture in the western part of Japan, facing on Seto Inland Sea here. And the other is Shizugawa Bay, facing on the Pacific Ocean. Both of them are very famous for their Pacific oyster farms. And each region have the 4 monitoring sites each. Even in the same region, they have the different characteristics in terms of the ocean physics and the biogeochemistry. For example, in a certain site that is closer to the river, so closer to the river mouth, so can be affected by the fresh water and the discharge from the river, the discharge of the organic matter from the river, and some are not so. So we did two methodologies. One is monitoring, the other is modeling. For the monitoring, we deployed devices to monitor continuously the temperature, salinity, pH, and dissolved oxygen. And alkalinity and dissolved inorganic carbon, DIC, were obtained from the water sample taken every 1 to 3 months. And aragonite saturation state, omega aragonite, was calculated from the observed temperature, salinity, alkalinity, and DIC. For the modeling, the next speaker, so the Lawrence Bernard will give the information much more in detail, but we use the fundamentally same model, which is a combined physical, biological, biogeochemical model. And biogeochemical model is based on a Pisces model, which is was developed by France team. And this is coupled with ROMS and regional ocean modeling system and the physical model. And we did present simulation and future projection. For the future, we targeted at the end of this century. So the 2090s with IPCC fifth assessment report scenario, two scenarios. One is RCP 2.6 and the other is 8.5. And we set some thresholds for to assess the impacts of the ocean acidification on the Pacific oyster, ocean acidification and ocean warming. For the ocean warming, in the future, the higher water temperature, the longer the spawning season can be. According to the previous studies, so if the water is getting warmer, the Pacific oyster can start spawning earlier in late spring or early summer. So based upon the previous study, we set assume the spawning, the start of the spawning season to be when the accumulated water temperature reaches 600 degree day, based on water temperature of the 10 degree. And the spawning season can end later as the water temperature is higher in the future. So we assume the spawning will end when the water temperature drops below 20 degree, based upon the previous study. And for ocean acidification, we adapted the previous study, which shows the threshold for the Pacific oyster larvae. Below this threshold, so omega aragonite of the less than 1.5, the oyster larvae can be severely affected by ocean acidification. So we assumed this as a threshold for ocean acidification. For the monitoring, this is the scenario of our monitoring. So we collaborate with fisheries people and the fisheries association. So the fisheries people, and we deployed some devices. So here are 3 devices: pH sensor, dissolved oxygen sensor, and temperature and salinity sensor. So we deployed for a long time. And this is the before the deployment. But 1 month after, depending upon the season, but in summer, especially, so many marine organisms are attached to the sensor. So we need to be very careful to get the accurate data. Otherwise, biofouling will affect the quality of the data. So move on the results. So the first monitoring results. The figure shows the time series of the pH first from August or September 2020 to the end of 2021 in the Hinase region and the Shizuoka region. The dots in a different color shows the data obtained from different sites in each region. So you can easily see that sometimes the pH is as low as less than 7.7 or 7.6 already. And sometimes the value appears during the spawning season or the larvae season. That can be the problem because previous study shows the spawning, the larvae season. Larvae stage is the most the ocean acidification appears. The larvae are affected most seriously by ocean acidification in the entire Pacific oyster life stage. So the season of the low pH and the spawning or larvae season overlapped. That can be the problem. And we found and the value is lower in the region when the sites which is closer to the river mouth. So we so far based upon the results, we consider that the freshwater discharge from the rainfall and the river can affect the pH and omega around, which I will show later. And CO2 increase the CO2 in the coastal water can be enhanced by the dissolution of organic matter from the rivers. So there to know more, we need more data, but there are some trends or the results show us such trends. And this is a similar figure, but for omega aragnon. This time, so we set a threshold for the Pacific oyster larvae. So once the omega aragnon is getting to be less than 1.5, that can be severe condition for them in terms of ocean acidification. So again, in Hinase, especially sometimes they will experience the lower severe condition of the ocean acidification. Especially the bar chart, black bar chart shows the rainfall. So sometimes the drawdown appear just after the rainfall. So obviously that can be considered to be caused by the freshwater discharge from the rainfall and riverine water. And again we are wondering if the riverine freshwater and organic matter can affect or accelerate acidification, which is kind of the coastal acidification rather than ocean acidification. And I move to the projector impacts of the future projection of the pH and omega aragnon. So here 3 lines. This is the black line shows the present simulation, and there are the other two for future. But one in a blue shows the value for 2090s, but for RCP 2.6 scenario, which is the scenario following the Paris Agreement. So the scenario we really want to need to reduce CO2 emissions from human the human activities. And the other is getting to be the kind of the business as usual, but highest CO2 emission scenario. So obviously the pH is getting to be the much pH and omega getting to be the much lower with a higher CO2 emission scenario by the end of this century. And in Hinase, especially by the end of this century, unless we cut CO2 sufficiently, they will experience the permanently low omega than less than 1.5. So that will be the severe condition for the Pacific oyster larvae. So needless to say, to prevent from such a severe condition, we need to reduce CO2 emission. And also the global warming may affect. So there, as I mentioned before, they may alter the spawning season. So the higher the water temperature will be in the future, the longer the spawning season will be. So the earlier start of spawning season in the future, and the later end of the spawning season in autumn or early winter. So the combined impacts of the ocean acidification and rising the water temperature can interact each other, and also may affect oysters in the future. So more severe acidity condition for in the future, and also the longer spawning period that may shorten the oyster sipping period and the lower quality of the oysters in the future. This is because if they, the adult oysters possess the eggs in the body. In Japan, I don't know in the other countries, but in Japan, generally speaking, they are not so attractive by the consumers. So in the future, not only the ocean acidification, but ocean warming may affect as well. So yeah, this is just a summary. So I'll stop here. But yeah, what I need to say is the mitigation is important to cut the CO2 in the future. But on the other hand, local adaptation measures, they're based upon our study, probably one of the solutions can be to regulate the fresh water and organic matter inflow from the rivers and the change of the oyster farming form. And yeah. So I'll stop here, and thank you for your kind attention. So yeah, we'll accept questions later. But if you have any urgent questions, so there are one or two, yeah, I'll accept. But otherwise, I invite next speaker, Lawrence Bernard. Is it okay?
Okay, for me it's fine.
Thank you. So the time is yours. So Lawrence is the postdoc researcher in here. So the Atmosphere and Ocean Research Institute, the University of Tokyo. Yeah, actually the colleague of mine. So yeah, he's a great modeler. So yeah, he focused on modeling results. So yeah, time is yours.
Okay, so can you hear me? Can everyone hear me?
Yes.
Okay. So okay, let me start my presentation. So I would like to talk about like one of the works that we have related to like ocean acidification, which is like the development of a high resolution marine ecosystem model for predicting the combined impacts of ocean acidification and deoxygenation. Okay, so first of all, this work was like initiated mainly to support a project called the Beach Project, which is the study of biological effects of acidification and hypoxia. So this was a multidisciplinary project featuring tank experiments, genetic experiments, and monitoring. And in my case, in our case, so we formed like kind of the modeling arm of this. So how to support these other multidisciplinary studies through the use of numerical methods such as modeling, and hopefully reproduce the present situation and make projections for the future. So the methodology we followed was first, we initially developed this approach for a pilot site, which will be Miyako Bay. And through this project, we had some monitoring data and with which we could like combine with our model results and further investigate phenomena. And then within this framework of the same project, attempt to look at other sites around Japan. Okay, so as I mentioned, the study site that was chosen as like the pilot is Miyako Bay here in the northeast like coast of Honshu, Japan, in Iwate Prefecture. So it's basically in a rural area, but it's well known for its like fisheries, and there are some local tourist spots, but also supported by rich fisheries such as the abalone and oysters. And with that availability of the data that I was mentioning, we selected this site to like perform a high resolution ecosystem modeling study. So first of all, while looking for the proper model to use, we found that the Croco system like was able to couple ROMS, the hydrodynamic model, with the Piscus biogeochemical model, which has the components which allows us to both study ocean acidification and deoxygenation. And in our case, since we are studying a relatively like a small site, like we also attempted to go to the higher resolution by using a nesting scheme. So first have a regional, capture the regional area, and then use this larger model to create boundary conditions and get more fine scale features in the finer scale grid. And first we set up to develop the present day model, which these are using these sorts of data for bathymetry, JEBCO, and we first initially used the 3R HICOM global model as initial and boundary conditions, tidal forcing from like TPXO7. And we also had realistic atmospheric forcing from the Japan's meteorological agency, which had provided hourly outputs from their mesoscale model. And we had also used sources such as the World Ocean Atlas and Almond and Bob for initiating the biogeochemical components. And since this is relatively close to the coast, or it's a coastal area, you have like possible influence of rivers. So like looking at our study site, we saw that there are 3 rivers that are like inputting into the site. So we tried to collect as much data as possible for flow as well as like measurements of nutrient loads. Unfortunately, these are not very large rivers, so like there wasn't too much data. So, but we did do our best with what we are able to find. And then we set up and ran the simulation for this period for a bit more than around a year and a half. And then through the modeled variables, it allowed us to calculate the model would output temperature, salinity, total alkalinity, and DIC, which we could use to calculate the carbonate parameters, pH, and omega aragonite. And as I mentioned earlier, this project also had a monitoring site here at the northern part of the bay, which allowed us to help to validate our modular outputs. So here is comparison between the observations, in black dots, versus what the model was able to simulate, and we see that essentially the model could capture the general trends and could have a pretty good reproduction of the physical states for temperature and for salinity, except that I guess for the salinity, we can see that during the summer months, we see some drawdowns in the salinity that are not captured by the model outputs. If we look at the carbonate parameters, okay, the pH and omega aragonite, we have some observations, and if we compare them to the model results, we see that although there are some periods that we can have a good match, but during the summer, again, there are some drawdowns in pH and omega aragonite that it seems the model is not able to capture, indicating some process that perhaps the model will still will need to be added to the model so that we can have a better representation or reproduction. Yeah, unfortunately, due to sensor problems, we could not get observation data for this winter period or spring to winter period, but I mean, that's all part of the process. We also have encountered difficulties in the field. And well, from that present day model, we then proceeded to try to create what you call future projections. And for these, we found that the JAMSTEC, which is aerospace and ocean agency of Japan, has been working on a 2-kilometer model for the entire Japan, which has some future projections for the end of the century under various scenarios, like the historical RCP 2.6 and 8.5. And we are able to obtain this data and also use them as initial and boundary conditions to run future projections for our study site. And the result of that is this. So you could see the observations and see how, for example, temperature, of course, would be expected to be so much higher at the end of the century for the RCP 8.5 scenario. And it's just mirrored by a decrease in pH as well, the how severely the ocean will become acidified. And in terms of what you can say is that the future projections suggest a significant impact of both the global warming and ocean acidification on calcifying organisms in Miyako Bay. So especially for RCP 8.5. And we'd like to indicate that the threshold mentioned for abalone, which is in Onitsuka et al. 2018, says that from their tank experiments, they found that abalone larvae can severely be affected for omega aragonite values less than 1.1. And we find that for our worst case RCP 8.5 prediction, this threshold is reached for much of the year. Again, this is also a model that attempts to predict what will happen with the oxygen. And as we can see from the result, there is some decrease in oxygen with the future, but they're still largely above the known threshold. But this is again for the surface, and the situation might be more complicated. In addition, we found that perhaps our boundary condition setting for making future predictions for dissolved oxygen are still not sufficient. So this continues to be a work in progress. And there are like other details, but that I haven't said here, but we invite you to view our recently published paper in Frontiers in Marine Science to capture the whole story. And as I mentioned, we've been trying to use this approach to see how it will do for other regions. And one of our numerical tests has been for the Tokyo Bay. It's like vastly more polluted and a bit larger in scale. And for Tokyo Bay, there has been a long-term monitoring site at the Kawasaki artificial island, which we have been using to validate whatever model results we could get. And here are some of our outputs from the model. So we can see that the model captures the trends at some parts of the year, but there are some parts that there's a larger mismatch. Again, the summer period seems to be kind of difficult or challenging to model for us at this time. Similarly, we attempted to make the future projections for Tokyo Bay as well, and these are what it shows. So the DO predictions don't show much variation. And as I mentioned, there must be needs some improvement for this particular way of making future projections. But it's all of work in progress, and at least we're happy we have been able to start somewhere to see how we can get better and better future projections. So ongoing and future work is that we realized that freshwater and nutrient loads into the coast may be underestimated in many of our models, especially during the summer season. But partly this is due to how I guess the lack of data, especially for smaller rivers. And another thing that is kind of difficult and to find data for some sites is the possible influence of groundwater discharges. And as I mentioned, the further consideration is necessary to improve initial and boundary conditions for the dissolved oxygen future projections. And of course, not all sites are the same, although we want to have a uniform approach that allows us to compare various sites there. Each site will probably need some a specific attention. For example, some sites may require more complex representation of bottom layer processes. And in the Tokyo Bay, which highly eutrophic comes to mind. So with that, these are the sponsors of our study. And with that, I thank you for your kind attention.
Yeah, thank you, Lawrence. So, any questions? So you can raise your hands or just put a question in a Q&A box. No questions so far? Okay. So, what? Any questions? Okay.
Okay.
So, yeah, we'll have the discussion session after all the speakers. So, thank you, Lawrence.
Yeah, thank you. Thank you so much.
Move to the third speaker. We have the two Ono-sans, but first Ono-san. So the Dr. Tsuneo Ono. Dr. Ono is a senior scientist of the Fisheries Research Institute, Japan Fisheries Research and Education Agency. So he's talking about most monitoring in coastal areas. So time is yours, Ono-san.
Okay. So thank you for giving this kind of great opportunity for the introduction for for introduction to our studies. I'm Tsuneo Ono from Japan Fisheries Research and Education Agency, and followed by the two talks regarding the specific local studies. I will introduce some feature of long-term and short-term trend of the or variation of pH among the Japan coast. Let me share my slide. So, and can you show this slide? Okay.
Could you do the presentation mode?
Okay. How is it?
Yeah, that's
okay.
good. Thank you.
So let's start. Okay. Like as many other coastal areas on the globe, coastal waters in Japan are also faced with the affection of global ocean acidification. The left graph shows the time series of the two longest time series stations in the Japan coast, operated by the Marine Ecology Research Institute. In these stations, pH had decreased at a rate of 0.003 per year in Japan Sea, and at a rate of 0.007 per year in Pacific coast. These rates are a little bit faster than the global average of 0.0018 because these two stations received both affections of atmospheric CO2 increase and water temperature increase. And we can also obtain signals of pH long-term trend from the data of over 2,000 stations operated for the regular water quality monitoring program of Japan Ministry of the Environment since 1980s. The right panel shows the histogram of long-term pH trend calculated in each water quality monitoring station. As you can see, the trend has remarkable variation from minus 0.02 per year to plus 0.02 per year, depending on the stations. This range is equivalent for around 85% of that obtained in 83 coastal systems in the world, collected by Carstensen and Duarte 2019. Despite of such large variations, average long-term trend over whole stations become minus 0.0015, which was almost same as the global average of ocean stations. This result clearly shows that the coastal waters in Japan is affected by global ocean acidification, while its rate in each station has wide variability under the influence of various coastal processes. If we look at the geographical distribution of long-term pH trend, we can see that the most stations have a negative trend along the coast of East China Sea and Japan Sea. These areas have been faced with severe warming in recently, so insight pH data tends to have negative trend in these areas. On the other hand, in Pacific coast, both positive and negative trend is observed even in the same area, indicating that very local processes are affecting to the long-term trend of each station. If we plot long-term trend of pH with that of total nitrate, we can obtain weak but statistically significant negative trend between them. This result shows that the extent of nutrient loadings in each area has certain affection to the pH, and hence the negative pH trend is relaxed in the area where nutrient loadings has been decreased. Since the water quality monitoring is basically operated bi-monthly or even seasonally, we cannot determine short-term variation of pH from the water quality monitoring data. So now we are starting to synthesize data of each continuous pH monitoring stations introduced in Fujii-san's talk to investigate features of short-term pH variation among the Japan coast. This is an example year-round data of pH and omega aragonite collected at 5 monitoring stations in temperate coastal areas in Japan, including Hinase and Shizugawa. As you can see, both parameters show significant short-term variation with the timescale of 10 days, as well as the seasonal variations. The amplitude of short-term variations is especially high in 2 stations in Seto Inland Sea, where both river input and nutrient loadings are relatively high compared to the other three stations. And in such short-term variation, omega aragonite values sometimes become lower than the threshold value of some marine organisms, such as Pacific oysters. Although the duration of omega aragonite violation under the Pacific oyster threshold is only several days per event, but it might matter to the oyster larvae because several rearing experiments show that very short-term violation of even several hours can increase mortality and abnormality of mollusk larvae. Fortunately, no abnormal shell of oyster larvae has been found in Japanese coastal area so far through microscopic inspection. But we should note that in future, length and frequency of temporal threshold violation will increase if we cannot stop the progression of global ocean acidification. But at the stations where the amplitude of short-term pH variation is small, temporal violation of omega aragonite threshold have not been observed so far. So the important point at the present Japanese coast is to identify the processes that determine the amplitude of short-term pH variation. And by looking at the detailed temporal variation of pH at the timing of short-term pH drawdown, we realized that most of such events had initiated just 2 or 3 days after the initiation of salinity drawdown, in other words, the rainfall. The duration of low pH period was longer by several days than that of low salinity period, but the duration as well as the amplitude of low pH event differs among event and stations. But also in most cases, enhancement of nutrient concentration was observed simultaneously with the initiation of pH drawdown. These features indicate that the main cause of sporadic pH drawdown after the rainfall is not the decrease of salinity itself, but some biological processes that is triggered by nutrient input from land delivered by the expanded river flow. To further investigate the variables that determine the amplitude of short-term pH drawdown, we calculated 10 days moving standard deviation of pH in each station. We then calculated monthly average of the 10 days moving standard deviation of pH and plotted that value with that of salinity. The left lower panels show the results of this plot for the 2 stations in Seto Inland Sea and the other 3 stations. In this analysis, we further added the data of Tokyo Bay as the end member of the highest nutrient loadings in Japan coast. And the results show that the slope of pH standard deviation against that of salinity differed among the coastal area groups. And moreover, the slope calculated in each area group showed significant positive relationship against the nitrate concentration of the rivers that flow into each area category. This result indicates that in temporal Japan coast, amplitude of short-term pH variation against the same size of salinity drawdown is roughly regulated by the amount of riverine nutrient input at the timing of the high river flow. It might be not only be dissolved nutrient, but like particulate organic materials that contains nutrients might also contribute to this process. Many Japanese scientists are also working on subarctic coastal areas, and there, significant effect of seaweeds and seagrasses to the diurnal variation has been detected. In the case of Oshoro Bay, diurnal variation of pH sometimes reaches to over 0.4 due to large biological activities of seaweed. In Akeshi Lagoon region, on the other hand, it is found that the diurnal variation of pH becomes about 2 times higher than in eelgrass bed than that observed in outside of it. But nevertheless, the numerical simulation indicates that daily minimum pH becomes higher in eelgrass bed than that outside of it, because high carbon uptake by eelgrass decreases daily average DIC value within the eelgrass bed. In subtropical Okinawa Islands coast, on the other hand, seasonal and diurnal variation of pH at the edge of leaf flat is continuously monitored. Here, response of several coastal species against acidification with the observed short-term variation are investigated by layering experiments. Not only long-term and short-term variations, but year-to-year scale variation of pH has also started to be analyzed in some coastal areas. For example, in Tsugaru Strait, significant decrease of pH at the rate of 0.003 to 0.005 per year was observed during the 7 years from 2012 to 2019. Detailed analysis showed that this high rate of pH decrease was accompanied with rapid increase of DIC and surface density, and these phenomena was attributed to the recent enhancement of vertical mixing between the Japan Sea deep water and surface water at the entrance of the Tsugaru Strait. As Masa said in previous talk, most of coastal pH monitoring stations in Japan had started very recently, and hence we are not able to carry out this kind of analysis for the interannual variation in most cases. However, in near future, we will expand this kind of analysis in many other stations so that we can get knowledge on the interannual variations of pH, as well as long-term and short-term variations. Now, this is a summary of my talk. In average, pH of Japanese coastal area has been decreased at the same rate of open oceans, but there is large area-to-area variability in long-term pH drawdown rate. In some area, pH is even increasing. By previous studies, it was realized that the long-term trend of pH has weak negative correlation with that of total nitrogen loadings. That is, pH trend is weak in the area where nitrogen loadings has been diminished with time. Besides the long-term variation and the seasonal variation, significant short-term pH variation with a time scale of about 10 days are observed in Japan coastal areas. And in most cases, these variations are associated with short-term salinity variation. Temporal violation of aragonite saturation threshold for some marine organisms sometimes occurs at such short-term pH drawdown event. But it is statistically detected that the amplitude of such short-term pH variation is diminished in the area with low nutrient loadings against the same size of short-term salinity variation. Other signals such as seaweed seagrass effect to the diurnal variation or local change in the vertical water mixing to the interannual variation are also obtained along the Japan coast. So we are happy if we can discuss about similarities or dissimilarities of these findings against the other coastal areas in the globe. Thanks for listening, and we welcome any questions.
Yeah, thank you very much, Dr. Tsuneono. Are there any questions? Yeah, the Ono-san. So there, yeah, there are, yeah, here's a, sorry. Here's one question there. So the Q&A.
Oh, yeah, I can see that. What could be the
yeah, please. So that what could be the major source?
Okay.
Okay, yeah.
So far we have only the concentration of the total nitrate data, so we are not sure about the source of total nitrate in each station. But in most cases, I think the total nitrogen comes from the anthropogenic areas, such as a city or farming ground.
Yeah, so there,
okay.
There, Dr. Kiran Kumar. So Are you satisfied with it? So, yeah, there are many sources, but largely different problem. Okay, so other question? One more. Yes, thank you. Yeah, okay, thank you. Thank you very much. So, any other questions? Otherwise, yeah, we'll again accept any questions in the discussion session later. So, thank you very much, Ono-san. And
Thank you.
yeah, the last speaker will be another Ono-san. So Dr. Hisashi Ono. Dr. Hisashi Ono is a technical specialist of the Japan Meteorological Agency. So he's doing the active measurement of the ocean acidification on in a open ocean. Yeah, rather open ocean. So time is yours, please. Yeah. So Hisashi Ono.
Fujii-san, thank you for the introduction. Let me share my slide. Can you see my slide?
Yes,
Yes,
we
we
can
can
see.
see it.
We can see
Okay.
that. Okay.
Thank you. Let me start my presentation. I'm Hisashi Ono from Japan Meteorological Agency, JMA. Today, I'm going to talk about long-term trend of DIC dissolved in organic carbon and ocean acidification in surface seawater of the western North Pacific. Not in the coastal ocean, but in the open ocean around Japan. This slide shows the contents of my presentation. First, I'll introduce JMA's observation about ocean CO2 system. And then I'll show you the recent outcome based on the JMA's measurement data. Let me start by talking about ocean observation by JMA. JMA has been routinely making shipboard measurements in the western North Pacific by research vessel, Ryofumal and Keifumal. Observation along 137 degrees line, which is the JMA's representative line, started in 1967 and has been continued for more than half a century. Our observation lines, including 137 degrees line, have played a part of courtship and GOA-ON. This slide shows the seawater sampling and measurements of inorganic carbon variables by JMA. We have collected seawater samples using CTD system from surface to 6,000 meter depth by operating a crane equipment. I also did that. After that, we transfer into the glass bottles carefully, and then measure ocean CO2 parameters and other parameters such as nutrients and dissolved oxygen. Regarding ocean CO2 parameters, we have measured DIC using colorimetric analysis since 1994, and total alkalinity, TA, and pH by spectrophotometric analysis since 2010 for TA and since 2003 for pH. Also, we have measured PCO2 in surface seawater. Since 1981, JMA has been regularly making underway measurement of PCO2 in surface seawater, taken from about 4-meter depth. For the measurement, we have used showerhead type equilibrator NDIR as a CO2 analyzer and CO2 standard gases calculated with WMO scale. And this is the distribution of PCO2 data since 1981 by JMA. From this slide, I'll briefly introduce a recent outcome about time series measurement along 165 degrees line. This left figure shows the location of JMA's measure observation lines and approximate locations of measure current. The 165 degrees line crosses various measure currents and fronts. From 50° north in the center of Western subarctic gyre to 5° south in the tropical zone. And we evaluated the long-term trend of DAC and ocean acidification along its line. For this evaluation, we mainly used measurement data of PCO2. This figure shows the year latitude distributions of PCO2 and DAC. Color shows the season. As you can see, DAC data is spatially and temporally sparse. So we calculated DAC, pH, and aragonite saturation index omega from PCO2 measurement data and alkalinity estimated values. Next, I'm going to show you how to estimate total alkalinity and calculate DAC. This left figure shows the marginal distribution of total alkalinity normalized by salinity, NTA, SSDH, sea surface dynamic height, surface salinity, from 50° north to 5° south. And the values of NTA were spatially and temporally almost constant south of subtropical zone and in the western subarctic zone. So in these two regions, we used average of NTA at each region. In the subtropical to subarctic zone, NTA varied spatially and temporally, and they were consistent with the variabilities in SSDH and SSS. So we made an empirical equation for NTA using SSDH and SSS in reference to the previous study. Then we calculated surface DAC from estimated NTA and PCO2 measurement data. Next, I'm going to show you about how to estimate DAC trend. This left figure shows the time series at 30° north as an example. PCO2, NDAC, NTA, SSD, and SSS. Black circles indicate measurement data, and red circles and gray lines are estimated values. As shown in the previous slide, we calculated DAC from PCO2 measurement data and NTA estimated values, like these black red points. Here, we found significant relationships between NDAC variability and SSD variability at almost all latitudes. and between NDIC and SSS in some latitude. Regarding SST, we think the relationship means the seasonal variation of DIC by vertical mixing in winter and biological activity in spring to summer. As for SSS, we think the relationship means the internal variability by the circulation change in the subtropical zone to subarctic zone, and ENSO in the subtropical zone. Based on these relationships, we applied MLR analysis to NDIC using time of year, SST, and SSS. This coefficient CD1 shows the linear rate of NDIC increase by mainly anthropogenic CO2 uptake. Applying this method at all latitudes, we estimated NDIC trends along the 165-degree east line. This is the result. This figure shows the regional distribution of DIC trends from 1996 to 2019. Red circles indicate 165 degrees line, and blue ones are along 137 degrees line as a reference. And black line is DIC trend estimated from the assumption that P-shots increase in surface water equal to that in the overlying atmosphere. And the rates of NDIC increase ranged from 0.09 to 1.64. And that showed clear regional variability, which was higher in the subtropical zone and tropical zone, and lower in the subarctic zone. And the variability was generally consistent with those expected from P-shots air increase. But, which probably means that DIC trends predominantly reflect anthropogenic CO2 uptake driven by the atmospheric CO2 increase. But the significant discrepancies were found in some regions, such as the center of western subarctic gyre and southern part of subtropical gyre. Why are there differences? In the next, we discuss the causes of the differences. First, let me show you about the western subarctic gyre. The NDIC trends were lower than those expected from P-shots air increase. Also, they were not statistically significant. Why did not NDIC increase during this period? One possible factor is the change in the atmospheric and oceanic circulation. Previous study had shown that recent weakening of Aleutian low causes the shrinkage of western subarctic gyre and deepening of main pycnocline. Actually, we confirmed the change in SSTH and pycnocline at 50 degrees north, although the figures are not shown. So we think DIC entrainment by winter vertical mixing weakened as a result of circulation change, and that made surface DIC relatively lower recently. In the next slide, we discuss the southern part of subtropical gyre. In this region, DIC increase was significant, but obviously lower than that expected from atmospheric CO2. The tendency was also seen at 137 degrees line. We think the possible factor in this case is also the change in ocean circulation. Some previous studies showed the southward shift of subtropical gyre in recent years, and which made the icy poor surface layer relatively thicker in the southern part of subtropical gyre. We think that the surface layer along the 165 degrees line also became thick, and it reduced upward supply of the icy-rich subsurface water, and it decreased the icy trend. Lastly, we show ocean acidification trends along the 165 degrees line. We calculated long-term trends of pH and omega from the acid trends and estimated total alkalinity at each latitude. Reflecting marginal distribution of the acid trends, acidification trends were higher in the tropical and subtropical zone and lower in the subarctic zone. The pH trends ranged minus 0.0023 to minus 0.0281 per decade. The range of pH trends are good agreement with global acidification trends published in IPCC 6. I'd like to finish with this summary. We estimated multi-decadal trends of DIC and ocean acidification in subsea water based on the shipboard measurements since 1996 along the 165 degrees line in the western North Pacific. And we found clearly regional variabilities in the trends of DIC and acidification. And they were generally consistent with those expected from atmospheric CO2 increase. But in the center of western subarctic gyre and the southern subtropical gyre, they were significantly slower. And they were attributable to the variabilities in ocean circulation. Finally, there is a question: will these trends found in this study continue in the future? In order to answer that, we have to continue time series measurements. So that's all. Thank you. Thank you all for your patience.
Thank you very much, Dr. Hisashi Ono. So, do you have any questions? If not, I have one. So they're really fun. So, yeah, in the last slide, you mentioned the necessity of the continuing your monitoring in the future. So, to answer this question, how long do you think need to continue the monitoring in the future? For example, tens of years. So you have done already last 25 or 30 years. But do you need? Yeah, of course, that we know the longer the better. But to answer this question quickly, so how do you think that?
Yeah, thank you for the question. Yeah, as possible as have to continue, but for example, in the subarctic gyre, western subarctic gyre, significantly slower trends and no trends were found. So, and the possible factor, for this is recent weakening of Artificial law, and to confirm this possible factor, we have to continue at least 10 or 2 years, I think we need.
Mm. Yeah. Yes. So thank you very much. And we have the one question from we have seen that the time of emergence varies greatly between. Okay. So I'll read the question. So the question is that's not only to the Dr. Hisashiono, to all speakers, but so the question is so you can see the chat, but if you can tell apart the anthropogenic signal from natural variability in the coastal carbonate chemistry, provided mainly to the Dr. Tsuneono. And you can.
It's a very difficult. Thank you for this important questions. Yeah. In the western part of the North Pacific, there is significant bi-decadal oscillations, and all coastal, including coastal systems, all ocean conditions are affected by this kind of interdecadal variability. So I think as long as 20 years, at least over 20 years time series will be needed to determine apart the natural variability and anthropogenic signals. And but there is another problem for the anthropogenic signals itself. In the coastal areas, there is two anthropogenic signals. As I shown in the previous slide, both temporal variation of the nutrient input and atmospheric CO2 variation cause the anthropogenic signals in the coastal areas. So we can also the two natural signals and anthropogenic signals, we also need to determine or divide the signals of CO2 concentration change and the nutrient concentration change. It is far more difficult. So at least we need the time series of pH and other carbon chemistry data, and also other ocean parameter data, including nutrient and oxygen and biological data as many as possible to determine and analyze such kind of conflict signals of long-term trend. And as you can see, the time of emergence is a very good idea to determine the long-term change from the natural variability. But as I said, that long-term variability itself contains two kinds of anthropogenic signals. So it is not enough to determine the time of emergence. We should analyze other one, long-term change in the coastal acidification and long-term change in the global acidification, I think. Is this make sense for the Katrina's questions?
Yes, so the Katrina, is that good for you? So thank you for the answer. Yeah, so and also the first we is getting the time to define what is anthropogenic. So there not only the CO2 emissions, but coastal for the coastal acidification. Yeah, of course the nutrient input and also the riverine discharge may be the important as well. So and yeah, this is so that we still have the 5 minutes, and can I share the slide?
Silvan has raised a hand.
Okay, sorry. Yeah, I didn't notice. So the Silvan, could you? Yeah.
Thank you. Can you hear me?
Yeah.
Okay. Thanks for extremely interesting talk. and very much you highlighted the difficulties, I think, in monitoring and predicting acidification in coastal environment. But so my question, and slightly now, Ono-san kind of reply, but what parameters we should monitor to get better prediction, especially? Because you talked about like pH, of course, carbonate chemistries, and then like I think Lawrence highlighted the need of freshwater input, but maybe through salinity. So like, is there like a golden set of parameters that we should consider for monitoring?
One thing I would like to add to this is the change in the first level producer, I mean the phytoplankton and algae. Because
Okay,
phytoplankton changes the relationship between the nutrient and carbonate can change. So it should be also monitored.
Okay, so it's okay. So like yeah, okay, primary producer mostly mean like.
Yeah, in my case, from the modeling standpoint, yeah, I notice that like it's like very difficult to get like for example geochemical data for the riverine inputs, especially for the smaller rivers. And as Fuji Sensei showed, like it's you have the influence of the freshwater input on the oil pH levels, but then like we don't talk about, when we look at this, they're not actually from the large rivers which are well monitored, but more local rivers that are hardly ever like monitored. And actually it's been my idea that maybe to improve the modeling efforts, for example, it'd be great to have like more like a better monitoring of even these small areas, and even things that are not usually considered like groundwater. I know it's perhaps very challenging, but I mean to have a more, to be able to capture in the model like more completely what's happening, then it'd be so much better to have all these data. And I'm thinking it could be a venue for example, like citizen science, ask local people to like help take measurements if that's possible. So I mean, these are along the lines I've been thinking of to help with the prediction efforts. Thank you.
Okay, thank you. Lots of parameters to measure.
Yes.
Thank you very much.
But I myself realized the importance of the salinity. That's very fundamental, but not so much the well monitored. Yeah. So okay. So the one question to the Hisashi Ono. So the Ono-san is now in process of the answering, and also the Ogno-san's so the. Yeah, we only have the 1 minute. So, yeah, so the, Hisashi Ono, did you there?
Yeah.
Have
Okay.
you already? Okay, yeah.
Are you trying to write the
Okay.
answer?
Well,
Okay.
yeah, even a good as well if you answer in oral.
Okay. Thank you for the question. The first question about first question. When calculating rate, samples are taken at what depth? Okay. About 4-meter depth for PCO2 and 10-meter depth for DIC and total alkalinity. And using from these data, we calculated the rate. And second one is apart from atmospheric CO2, what factors cause the pH or omega trend to decrease? Yeah, basically, it's due to atmospheric CO2 increase, but they are affected by ocean circulation. So yeah, it's due to the ocean circulation or particle mixing or something. Yeah,
Okay.
Does it okay?
So they're asked by the anonymous presenter, the participant. So yeah, so that if you have the further question, please put in the chat. And yeah, Sarah kindly gave us additional time for 10 minutes. So Lawrence,
Yes, there's a question from so
Oguma.
from Sachiko Oguma. So thank you for your question. You'd like to ask if you're going to simulate more accurately in high resolution for Tokyo Bay. Okay, so the Tokyo Bay model was initiated as part of the beach project, which is something that like already finished like early this year. But of course, the setup is like still there, and now that we have been able to like publish our like approach for Miyako Bay, I think Tokyo Bay is also along on the line. It's more of that we're continuing to improve the setup. Of course, it's much more complicated to the challenge with Tokyo Bay, for example, is how do you accurately capture the nutrient loads from the river? So when we were in the process of modeling, it was like a struggle to us. So you know that not only the sewage, like not only the actual river nutrients, but also the impacts of sewage. So these were some of the challenges that we were looking at while developing that model for Tokyo Bay. But because it is an important site, so I imagine that we will indeed continue to like work on this setup and try to find ways to improve it in the future as we go along. And I hope I answered your question.
Yeah, I hope that. Yeah. So thank you, Lawrence. So are there any questions? So if not, so that, can I share the screen? Okay. One more question. Okay. No. Okay. So can I share the screen here? So yeah, because in today's presentation, yeah, actually there are most of the results in the presentations are already published. So you can see the publication this year. And also, yeah, so do you see the screen? So today, yeah, we discussed about the importance of the maintaining long-term monitoring with sufficient accuracy. So I think that in Ono-san's presentation, so there are huge daily or short-term fluctuation on the pH, but partly, I think that partly caused by the biofouling, right? So probably we may need to distinguish the kind of the fake fluctuation caused by the biofouling from the natural fluctuation. So that can be done by the improvement of the technology. And also each of the both on the monitoring and the modeling need higher spatial temporal resolution. So that's otherwise we cannot take riverine input into account. And this is as Lawrence mentioned. And also this is one of the one session among the GOA-ON project. And we always need to consider about the collaboration with the society or support by the society. So we talked about the situation in Japan, but we don't have the sufficient support by society, not society, but especially from the any level of the government. For example, the many countries already have their action plan on ocean acidification, but we don't have. So, provider, we need to know each other to move forward to tackle ocean acidification. And yeah, any other comments from the audience or presenters? So that who is raising hand? Is that Silva?
Yes,
Okay.
it's okay.
Please.
Just a very short question, like I think it's to be impossible to have a high spatial monitoring all across Japan, but do you think there are some areas that should be mostly targeted? I mean, there was Tokyo Bay. I can understand Tokyo Bay for high anthropogenic effects also, but is there some areas maybe like that are understudied that should be made a priority?
Okay. Yeah, I have some questions. I have some comments, but first I'd like to invite Dr. Tsuneono about
For the coastal area, you mean?
Yes, for coastal areas.
Okay. First of all, I would like to emphasize that the Japanese contains many climate area from the subarctic to the subtropics. So obviously, we should set at least one stations in each climate areas. I mean, the subarctic area and the subtropical area, and also the temperate area. And we have in Japan, as I said, there is a large variability of the anthropogenic input along the coastal areas. Some coastal areas has even natural, almost no anthropogenic input from land. But as Tokyo Bay and Seto Inland Sea, we have many amount of the nutrient loadings and other anthropogenic loadings is included in that kind of bay areas. So we also set the series of the monitoring stations along with the different amount of the new anthropogenic loadings from no loadings or to the extremely high loadings. And now we are able to get such kind of series of lines, stations, both for the climate and both for the anthropogenic loading is in the present station designs. So what is important will be to continue these set of stations along the Japan coast.
Yeah,
So maybe increasing quality over the quantity may be more important.
Yeah, quality, especially the biofouling problem is more very important for get very accurate variation. Especially for the diurnal variation, we already recognized that diurnal variation has affected severely from the biofouling. We can get the signals of the day-to-day variation even under the biofouling, but we cannot for the diurnal variation. So it will be very important to very short timescale variation analysis.
Thank you.
Okay, so yeah, so the time's up. So we can continue to the discussion by emails if possible, and so I'm sorry that we need to close the session. So thank you so much, and for the speakers, audience, and Sarah and Katerina, and we close the session and enjoy the rest of the sessions in this week. And for some countries, happy Halloween. So yeah. So
Thank you all.
yeah.
Yeah.
Thank you so much.
We would really like to thank the moderator and speakers for this great session. And thanks to the audience for your wonderful questions. This was such a great overview about OA in Japan, from the oyster farming to the chemical monitoring in coastal and oceanic zones, as well as the modeling. And it was a wonderful overview. So thank you all. We still have many more sessions with OA Week, so please consult the website, and we would love to see more of you at our sessions later this week. If you would like to stay up to date with GOA-ON, again, please visit our website and consider signing up as a member. And finally, as a member of GOA-ON, I would like to plug the Ocean Acidification Research for Sustainability program. This is a UN decade endorsed program, and it is accepting commitments for OA action. So this is a call to the entire OA community to check out this wonderful program and consider becoming involved. You can use the QR code or the link that I believe is in the chat to discover more about this great program. So thank you all, and see you again next time.
Thank you so much.
Thank
Thank
you
you.
so much.
See you. Bye-bye.